funny guy, Felix.
I would be so mad with my life.
You're a funny guy.
If I'm like, God, I'm trying to find it. Because it's not really fun. But are you seeing eating all the it's the best.
Carlitos, look. We go. Look, it's you and me, bro. That's Spanish. That's in the Huh? You can break dance pretty well. You just have to be drunk enough, and then I can dance pretty good. Huh? What? Oh, yeah, no, I said as long as she's drunk. The drunker she gets, the better I get at dancing.
Oh, I want to go. Can we go?
Yeah, it's like $1 to get in, I think. I don't know if you can throw a drink for free, but it looks cool. 101?
Oh, it's on.
Really? No, flip it.
Probably we will not be using computers anymore, I think about it.
We're done with computers?
No, we're not using computers today. We're definitely using computers on Monday. All right, time to get started. So, if I have a stable linear system,
What's the name of this one?
if my input
I don't know. Wait, what are we doing now?
goes to a new steady state, if input, for example, does that,
What did you say this was called? This is a new thing, new subject?
Fritz, I like the titles. Then the output might do a oscillation, but ultimately reaches a new steady state. On the other hand, if the input is periodic, the output will never reach a stable state. We're talking about stable linear system, something that has all poles with negative real
Right.
parts. Okay?
Question? No.
If I have all poles with negative real parts, that's what will happen if my input reaches a new constant value. But if my input reaches a repeating periodic function, which is sine and cosine, the output might do some things first, but ultimately it will end up with the periodic function. And interestingly enough, it will have exactly the same period as the period of the input. If this has period capital T, this has period capital T. But it will not have the same amplitude. What is amplitude is the height. This is the amplitude. So it will have the same period, but the amplitude will be different. Also, the input and output are not going to be in phase, meaning the maxima and the minima will not be happening at the same time.
That's due to the delays.
Not only just the delays. Delays are part of it, but even with the zero delay, that still wouldn't be the case.
They're not what? I didn't catch that.
They're not in phase. They're not coinciding in time. If I were to plot input and output on the same plot, this is the input, the output would be lagging behind. So this is input. Output on the same plot might be so the period is the same, but the maximum don't happen at the same time. This distance between maximum of the input and maximum of the output. Minimum of the input and minimum of the output. The period is the same, but they have different amplitude and they are not in phase. The output lags the input. The behavior of the output for a periodic input depends on the frequency that is being used. Frequency is equivalent to the period of the input. And the subject matter we're entering now is studying the effect of that frequency, and this is called frequency response. That's what we wanted to write. One, let's write it.
I don't think so. Is it really?
Since I'm talking about a linear system, that means I have a transfer function representation. So let me do the input on white and the output on orange. So here's my system. And let's say this has transfer function g of s. Okay? And if the input is something like that, the output would be same period but different amplitude, so it could be amplitude could be bigger or smaller. Okay? So both would have the same period, let's say. And let's call the amplitude of this A and the amplitude of this B. So these are the amplitudes of if you have a sine or a cosine. So the input, and let me write Z for input. Z can be anything, any input, U, a disturbance. If we talk about closed loop system, could be the set point of a closed loop system, but let's say for open loop transfer functions. So input, for example, could be Z of t equals A sine omega. Omega is the frequency, and the period is related to omega by 2 pi over omega. Some question?
Usually, I would guess the angular velocity, right?
No, frequency. We are not with angular velocity in this class. It's the frequency of the oscillation. How many cycles per minute, per second, whatever. Omega is for angular velocity, but you also for a lot of other different things. The output y of t will be v different amplitude sine, and I can rewrite that omega t plus phi. Phi is the lag okay. The lag controls how much this. The output can be read. This is the input. I should say, what? I say the output. I should say put here the correction, guys. Output.
You say phi, or is that a phi? You said that's the, what is that called?
Phase length. We'll talk more about it in a minute. One correction here. As I showed in that picture, you don't go immediately to that response. You go to this response eventually after systems die out. Some people use the term periodic steady state. I hate that term because one of the things that we have been trying to ingrain to you through our biochemistry curriculum is steady state means flat line. So I hate to use periodic steady state for something that is not a flat line. It's repeating oscillation. So I use the terminology ultimate state. Okay, so the ultimate state, instead of being a steady state, is repeating oscillations, the same oscillations. So ultimate output is that. It's what you have as time goes to infinity. It's going to be that. Okay? So you have a sine in, sine out. The frequency is the same. Omega frequency in, omega frequency out. However, the amplitude is different, and they are not coinciding in time, the maxima and the minima, as I showed. Here is a thing that is actually not too difficult to prove. I'll probably just walk you through. Should be tempted to assign the proof as a homework.
Oh,
We had time now.
no.
But I won't do that. Here is a very interesting outcome. The amplitude ratio which is the ratio of the amplitude of the output to the amplitude of the input. You can show that it's going to be equal to the magnitude of the complex number that we have if we replace S in the transfer function by I times omega, the frequency of the signal. And the phase lag, that phi that you see there,
What do those two bar mean? Is that the determinant or something?
no, that means magnitude of the complex number.
Magnitude.
So obviously you all know that stuff. I don't need to repeat it, right?
Yeah, I just don't know what's the.
I was trying to be funny and not being very funny. Obviously, I don't expect you to remember this stuff, so I will spend a little while. That's why we have not completed today, because I remember I have to do a review of complex numbers. So I'll do a review of complex numbers and you understand this double bar very clearly before the end of the day today.
What's G of IW? What's G of IW?
I'm missing what's saying after is.
What's G of IW?
It's G of S replacing S by I omega. So for example, if my G of S is K over tau S plus 1 e to the minus ds, G of I omega would be K over tau times I omega plus 1 e to the minus d times I omega. Wherever you see S, you put I omega. That's what I mean.
And what's I?
Square root of minus 1.
Okay.
Yeah, I here is square root of minus 1 for complex. And if you love the double bar 1, you love the next simple number. That's the argument of the complex number.
That one I never seen before.
You've never seen it before, guys? Come on.
I've never seen that one.
I've seen the double bar. I never seen that shit.
Yeah.
Didn't you deal with complex numbers, guys?
No.
Come on, you had some class that calculus 3 did that with complex numbers, didn't it?
No.
I don't even know what I don't know what you mean by complex numbers.
Imagine.
Imaginary? Oh, no, definitely not.
Imaginary means no real part. Zero real part.
Then imaginary and real.
Yeah.
A little bit of DPQ, but I don't remember. That's so many years ago.
You did?
All right.
The sine and cosine
Make a
shit.
question.
Does the double bar mean magnitude?
Double bar means magnitude, yeah.
Magnitude, there you go, magnitude.
Do you have
All right. So,
Do you have Ballword
For calc.
for
before I do the
Yeah.
semi, I'm going to walk you through the proof of that. Let's
We saw it again in
do a
transport.
review on complex numbers.
If
Okay.
you took, yeah, you took it with Chauhan, yeah.
Review of
The sine and cosine.
Yeah, but it was just a transformation.
Yeah, that's what it is.
He gave us a
okay,
transformation
complex number review.
from E.
Yeah, that's what. Yeah, that's it. That's it. Yeah. It's the same. It's just a way to.
Okay.
I don't know.
What is a complex number? A number has a real part and an imaginary part. For example, 4 plus 7i is a complex number. So possibility. Come on, you learned that in high school when you did the roots of a quadratic equation.
Yeah.
Okay? And so, and in this Cartesian representation, a plus bi is a complex. And we can plot a complex number if we have the x-axis for the real part, the y-axis for the imaginary part. I would plot the complex number 4 plus 7i as a point in this Cartesian space. So 4 plus 7i would have 1, 2, 3, 4 real part, 1, 2, 3, 4, 5, 6, 7 imaginary part. So it would be, this point here is 4 plus 7i. If I go 1, 2, 3 here, and 2 here, this point here would be minus 3 plus 2i. If I go, this point here would be 1 minus 4i. Clear, everyone? So we can represent any complex number in this Cartesian space. The magnitude of a complex number is the distance from the origin. So you can represent it as a vector. Okay? So you can represent every complex number as a vector.
The magnitude is the distance from the mid.
And the magnitude is the distance from the origin. So here that would be the magnitude of 4 plus 7i is that distance is the magnitude. And since this would be a right triangle, Pythagorean magnitude